Okay. So in the previous 2 hours, we have looked at very general view of what tools are available to you. And we have also seen the minor differences between various tools and also what they are used for. The next thing we had seen was various processes which are available. First of all, we wanted to distinguish between what is analog IC, RFIC, and MMIC. Next thing we looked at what's the difference between CMOS, silicon germanium, GAS, and GaN. And then we also looked at broadly what a MOSFET or PHEM does versus what a HBT does. Okay, so now there was a question whether, if I create something like this for your reference, I will pass on this to you. I'll pass on more material than what I'm going to show here for your study. Okay, so not an issue here. Okay, so let us go back to our presentation. Okay, and let's start with this. Now, this is a very, bird's view of what is required and what we are doing. Okay, first of all, there are 2 major areas where this kind of development is required. One is your communication systems. Okay, now the communication can also be a sensor network communicating to a network, and then that data is broadcasted to different locations. So that is basically all your IoT applications, right? There is a sensor node and you get the data and that's kind of stuff. Then there is a communication. So it can be voice or a data communication, right? So connectivity is the major area. The second area is going to be your defense or radar kind of area where you would do development. Now, I'm not going to talk about radars because we are focusing on communication systems and specifically 5G. So I'm not going to talk about that. Connectivity, you can see the scope. Like, you need a human communication. You need a human business communication, business to business communication, transportation. So there is a vehicular network which people are talking about. So basically, you can trace somebody's car, your family member's car, and you can communicate, right? So vehicular traffic is vehicular communication networks, right? That's also a form of communication. Inventory management, warehousing, everywhere it is required. Universities are availing certain services, so they need to communicate, right? Maintenance related cataloging, machine to machine communication. So there are different areas where connectivity is required. And you can look at the scope of this business. Okay, you already know how much is the cell phone business, right? So you see, we have an area which is very huge. And it's not that only one form of communication will be used. Like, we cannot have just optic fibers everywhere. Or let's say we cannot have the wired communication everywhere. We need to use satellites somewhere, right? So there are different forms of communication which are required to cover different areas. Now, what it means? It means that a designer basically has to know what he or she is designing for, right? So that's very important. So now from job prospects, there are lots of companies there, right? So of course, development companies, your design houses will be lesser in number, but if you see, there are lots of companies there. Universities, they do, all kinds of collaborations. So all this comes under connectivity. So there are technologies which compete, and there are technologies which basically complement. So if a wired technology is there, at some places you will find optics along with it. You will also find terrestrial wireless. You find satellite communication, right? So all these forms of communication are there. So when you are designing, you should know what you are designing for. Whether you are designing for a wireless link, which is used by satellites, whether it is a terrestrial wireless, okay, whether I'm going to do blocks for optics, right, or wired communication. So all these complement and compete, right? And let's say we are talking about 5G satellites now, right? So 5G satellites can be in the low Earth orbit or medium Earth orbit, okay? Or the satellites can be basically geostationary satellites where latency is not important. You can use geostationary satellites, right? So 5G satellites people are talking about, right? Terrestrial wireless, you already know that 4G systems are there now, 5G systems are there. People are talking about 6G systems and all that, right? So for all this, you need resources. And these resources are the most important resources, the spectrum, right? And then in the spectrum, they have done various frequency bands: L band, S band, C band, X band, Q band, K band, Ka band. Now, all these are important. Why? See, let's say if you are designing in Q band, or let's say Ka band, then what is near to those two bands is the K band. Why this K band is infamous? Because 22 gigahertz is what? Water absorption, right? So basically, whatever link you design, absorption by water becomes important here. So you will not talk of big cells, rather you will talk of micro or nano cells in a cellular network, right? So if you are designing for Q or Ka, you will be in cells which are very small, right? So that is because of that. Second thing is, if you talk of U band, Q band, and all that, right? They will be used for mostly indoor applications, right? Maybe they will be the last mile connectivity. Maybe they are used for satellites also. Geostationary satellites are being designed in Q and V band, right? Because the bandwidth goes up as you go higher in the center frequency. Basically, the bandwidth goes up, which means that the throughput rate goes up, which means that you can afford more services, more number of subscribers in a channel, right? You can have subscriber capacity can go up, right? So a lot of things can happen. A lot of things will happen, okay, depending on how, where you are, right? So this already crowded band is there, S band and C band, right? There are lots of already consumer electronics communication is all in C and S band, right? Now people are migrating to higher bands. So when we look at 5G, there is a sub 6 gigahertz 5G, which is being rolled out now, right? And then there is going to be another high speed 5G, which is going to be around Ka band, which will be like 24.85 to like 28.35. Again, it depends on country to country, right? For example, we have one big band, okay, for 5G in India, while in America you have like 27.5 to 28.35, that band. Okay, so it depends on where you are designing for. If you really want to keep a broadband system, right? So the band is an important resource. The spectrum is an important resource, and where you are in the spectrum, that changes the design complexity. It's not that they are complex here. The frequency is just a number, but you have to be careful about what you're doing. Okay, so frequency. So if somebody says, I'm a designer in QV band, and there's nothing special about it. It's just like your age. It's just a number, right? Similarly, frequency is just a number, right? So as a designer, you can approach the design in any band, provided you are careful enough, right? So if you're designed for QV band, nothing special in it. It's just that you have to be especially careful about grounding and stuff like that, right? So here, impedance control is important here. Okay, next resources we have talked about it is the semiconductor technologies. So basically, you have a lot of choices now. Earlier, we didn't have so many choices. So our circuit design used to be more complex because we have to work around a lot of stuff, right? But now the gate lengths are scaled down to like almost like 5 nanometer. Now you can do very high speed circuits in silicon. You do not need to go here, but then for power, you may have to go here, right? For power circuits, you are not here. So semiconductor technology is important. And the last one is the human resource. Now, and this is the most important one, because if you see, nobody becomes a king of all the technologies. It's like you can be jack of all. Like I am jack of most of the stuff, right? I'm not an expert in most of the stuff, but I'm a jack of all the stuff, or most of the stuff which I can see. So that's not how companies work. Companies would have people in clocking circuits, clock recovery circuits, PLLs, timing circuits. There will be a specialized group. Power amplifiers, low noise amplifiers, RF front end, that will be a separate group. Transceivers, that will be a separate group. Data is like analog digital conversion, digital analog conversion, basically, that will be a separate group. right? So different skill sets are required for different designs, and the system is made up of everything. So if you are a system designer, you are supposed to know everything, but not completely in detail that you can go ahead and design every circuit. But it's like, you know, the specifications, right? So you are supposed to know on a system level what you are expecting, and from the components levels what you are expecting. So human resource, again, this is a common training, but later on you will specialize in a different area. So I may not be an expert in all the areas, right? It's just that I try to experiment a lot. So that's there. So I'm going to assume that we are a mixed group and we are going to learn everything but a little bit, and later on we can specialize in a particular area. So 3 resources important. The spectrum is the most important resource for wireless. Semiconductor technology is a resource for our development, and human resource, which is you and me, the designers. Okay, wireless technologies, I started with 1G. And this is analog communication. This is mostly voice, and this is nowhere there is data. Okay, this was way back in like 90, 96, 97, 98, something like that. Now we from there I went into designing these 2G communications, like, you know, started with NADC, PDC, amps. In America, I was with IBM. I was designing NADC, PDC, and amps. Then I migrated to designing GSM parts, right? Power amplifiers, basically, DCS. Now, what's the difference between these? Okay, there are 2 basically categories in wireless. One is called the mobile standards. The other one is the computer networks. The computer networks is a point-to-point. So mobile network is not point-to-point. What is the difference between what is a point-to-point? When I don't need any other entity between the 2 points of communication, I will call that as point-to-point. So for example, if 2 computers talk to each other, they do not have a base station in between. Okay, they can directly talk to each other. That I will call point-to-point. Or in case of mobile, okay, we are not point-to-point because we need a base station in between. And what is this base station doing? Okay, so for example, I have a certain band. Okay, I'm transmitting in certain band and receiving in certain band, right? So this is a frequency division multiple SS. Let me just add people here. Okay, so there are multiple SS schemes. Like for example, how I adjust many subscribers in one system bandwidth. Okay, so there are 2 things which you should know. One is the system bandwidth, other is the channel bandwidth, right? So I might use different frequency for transmitting and receiving. Okay, so that will be frequency division multiple SS. Now, when I do that, right, I would have to allocate subscribers frequency channels in transmit band as well as receive band. So I'm transmitting in one band, I'm receiving in another band. There has to be an entity in between to do the translation of frequency. Okay, so that is what the base station is doing. That's what the base station is doing. In computer networks, it's mostly like time division multiple SS. Okay, what they do is, let's say there is a Wi-Fi bandwidth of 2.4 to 2.5 gigahertz. In this, there are channels. So I can have certain channels for transmit, certain channel for receive. So still there is a frequency domain dependence. But again, the people are talking in different time slots. So basically, this is a time division multiple SS. Okay, so a particular subscriber is allotted a particular slot in a particular frequency for transmitting, and a particular slot in that is a particular channel frequency for receiving. Okay, so that will be called time division multiple SS, right? Then there are Cdma technologies. Now in Cdma, what happens is, instead of using a carrier frequency as a carrier, a frequency, I would be generating a PN sequence. Okay, now what is unique about PN sequences? For a given size, let's say how the PN sequence is generated, it is generated by a left shift or right shift feedback register. So the PN sequences are just generated by shift registers with a certain feedback taps. Okay, we will, if I show you, PN sequence generator, I'll show you, right? So what is there? It is, you feed in a particular seed into a register, and that register basically is capable of capable of serial shift left or shift right. And then the from various locations I can pick up taps, and which I can combine and feed back, okay, on the left side or the right side of the shift register. That's how PN sequences are generated. So for n bit word, 2 raised to n PN sequences are possible, which are orthogonal. So what do I mean by orthogonal? It means that if I do a correlation function of two PN sequences, two different PN sequences, they are orthogonal, then the output is 0. Right? Now, if the two PN sequences are same and I do a correlation, okay, then the autocorrelation function is 1. Okay, so now this is like a key, right? So for example, let's say I want to do a CDMA call. Okay, so what does my phone do? First of all, it is going to send the seed information. There will be a handshaking. I will send a seed information. Seed information, the number of bits would be so large that I can go for hours for talking without exhausting it, right? So I will send the seed. Now, between transmitter and receiver, there is an agreement that we are going to generate same PN sequence. So if you are going to generate same PN sequence, when we are demodulating it, we get each other's information. But all other people who are allotted different PN sequences, they would not see our signal at all, because it is going to be just a white noise, okay, because the correlation function is 0. So that's what a CDMA is. So CDMA technologies came around here under 2G, right? And they are popular as IS-95. So what you call as mobile communication, that is going to be around 800 megahertz. Okay, then there is a 1900 megahertz, which is called PCS. Okay, so 800 version is called cellular. 1900 megahertz version is called PCS. For example, in India, Reliance uses a 1900 megahertz CDMA. It's the same IS-95, but they are using different carrier frequencies. So you are in 800 megahertz range or 900 megahertz range, this would be called cellular. If you are in 1900 megahertz range, it will be called PCS, right? So we had CDMA here in under 2G. We could do data transmission, we could do voice and all that. So these are all phone standards, right? So what was realized is the kind of bandwidth is like 1.25 megahertz kind of channel bandwidth, right? So basically your throughput is limited to that. So what they realized was that we need more channels now. So they clubbed three of them together. They call it 3GPP. This was like a certain data rate, which is like 3.84 megabits per second throughput, which is almost 3 times of 1.25, right? So they called it as UMTS 3GPP, or wideband CDMA 3GPP. Okay, and then there are two versions of it again. One is a Japanese version, other is the American version. American version goes slightly higher in bandwidth, like throughput rate, and then power levels are higher in case of American version. Japanese versions are like 250 milliwatt peak power. American versions like half watt peak power. So we started with data communication around 3G. Okay, 2G we had data communication, but that used to go through your GPRS edge kind of thing. Okay, so this is all CDMA technology. Then before that, we also have now mix of CDMA with GSM, right? So GSM is your regular, what you use. It's again a TDMA, but then it has got transmit receive bands, and you basically are allotted a slot in transmit band and a slot in the receive band. So that version at 800 would be called GSM. At 1700 version, it will be called 1700 megahertz version, it will call DCS. Okay, so these two flavors are there, right? So a lot of stuff was developed here. This was 1G was all analog, then 2G was digital modulation, right? And then digital modulation allowed a lot of other stuff, like for example, we could do forward error correction codes, and we could do block coding and encoding and all that. So we were able to basically add some noise immunity by some kind of a forward error correction code or block codes. right? So all this was developed in 2G systems, and this supported voice and data. In 3G, the major dominance was not on voice but was on data, and then broadband communication. So we were combining 3 channels, adding some additional scrambling to it, and we were calling it 3G, and it allowed a larger data throughput rate. Now coming 4G, there is a major difference between 3G and 4G, okay, which I'll explain in the next slide. Okay, somewhere in between they introduced WiMAX, right? Again, it's kind of a computer standard. It's not a mobile standard. Okay, Wi-Fi is all mobile. It's all computer standard, right? So 802.11 ABG came. Then after that, ADAC came, right? All that is Wi-Fi, and that's a point-to-point communication. You don't need a base station in. That's mostly like a TDMA kind of stuff, right? So that basically carried on to WiMAX. That is 822.16 ABCDE. Mobile version is called E. That WiMAX was in 3.3 gigahertz to 3.9 gigahertz band, right? So that WiMAX didn't pick up. Before it could pick up, there was 4G. And 4G, we do not have base station. We have access points, right? We have much like computer communication, right? Now, long-term evolution. Now, what is happening here between 3G and 4G is the following. There was a lot of channel estimation going on here in 3G. Like, for example, before I transmit something, I'll estimate the channel. I'll make correction for those channels, right? So there was a lot of channel estimation going on here. While in 4G, they started with something called OFDMA. Okay, so what is OFDM? Okay, so what it is if we have a very high speed data link, very high speed data rates, we will divide it into sub channels with slower data rates. And instead of using one carrier, we will use sub carriers, right? So how will we divide this into subcarriers? We want to divide it in certain way that the correlation between these channels, sub-channels, is near to 0. That means that the data is totally uncorrelated on these channels. So let's say if I take one high-speed channel and I divide it into 4 sub channels, right, or subcarriers. Okay, now these data-wise, they should be orthogonal. So basically what it means is that there is a uncorrelated information or data on all the channels. Okay. Now, if I send these together onto a wireless or a wire medium, then at the end, when I receive it, I will get all uncorrelated data on different channels, but I will also receive correlated information. Now, what is that correlation? Is correlated information? That is channel estimation. That is how MIMO is rugged. So it reduces to a eigenvalue problem. Okay, you have a data which is orthogonal, right? So basically you can take all the uncorrelated data and extract it out, but then you will also get the correlated data, and that correlated data is your channel estimate. So channel estimation became easier with what you call OFDMA. And this is what you do in MIMO also. In MIMO, instead of using one transceiver, I'm going to use, let's say, 4 transceiver, 2x2 MIMO. So I will be sending subcarriers on different transceivers. But when I receive them, I will try to extract the correlated information. And that correlated information would be the channel estimate, which I can compensate in each channel. And I have a very high noise immunity data link. That is what is happening with OFDMA or MIMO. Okay, that's the background for 4G. That's the background for 5G actually. 4G and 5G are like that. Now, going from 4G to 5G, what changed? It was realized that it is not efficient. You can tolerate certain correlation between the channels. So the subcarriers need not be orthogonal. So that means that you can have more data adjusted in these channels if they are not completely orthogonal. So that's the major difference going from 4G to 5G is orthogonality is not the do-die thing. You will allow certain correlation, and that way you can increase the channel capacity. That's what happened with 5G. Okay, now you implement the same thing at higher frequency under massive MIMO, that would be 6G, right? That's what I understand of 6G at present. Okay, I haven't read a lot of papers about it. Okay, let's admit lots of people are there getting. Okay, sometimes I'm in the middle of discussion and I forget to put in people. Yeah, I'm really sorry about that. People joining now, I'm sorry about that. What you have missed, you'll find in the recording, right? So I was discussing these different standards, right? So people are clear why we are going to MIMO and massive MIMO is because of the channel, the ruggedness to the noise. So it's not only the signal which we are concerned about. If there is a noiseless channel, then the data throughput rate would be infinite, right? Because I don't have to struggle against the noise, right? So that's the whole idea. How immune in a system you are to the noise, that basically will decide your capacity, right? So that's what is happening in 5G. Okay, now to sum this up, the next slide will tell you what's happening. Okay, so trends to improve spectral efficiency. Okay, if you need to transmit something back, if it is in error, that's the extra bandwidth you have lost. Your throughput has gone down, right? So you would use channel estimation, forward error correction, and stuff like that, equalization. Up to that point, we were okay. Next, we came with code division multiple access, that we started saying that, okay, interchannel interference can be minimized, or the subscribers can basically talk. Yeah, is there a question? Okay, well, I'll put all of people in mute. If you have a question, you type in here. Okay, so CDMA was a lot of improvement over what previously was introduced, because CDMA provided a lot of freedom from immunity from interchannel interferences, and then you would not be able to get the information of what somebody is transmitting. So it was more secure. Then going forward, when we went to OFDM and MIMO, a lot of things improved on the channel estimation side. We don't have to do that. We are working with, orthogonality here, and we are able to estimate the channel and subtract it out. So basically this is more like a principal component analysis. So your channels are your principal components, while your noise is basically correlated information. So you should be able to just subtract it out. And how do you do that? Well, there are some things called filter banks, and then coefficients are basically adjusted, and you are able to extract out the correlated and uncorrelated information. It's just like a subspace transformation. That's what I would say, that you can separate out a subspace where the channels are orthogonal, and then the correlated information separates out. So that is implemented using this kind of convolution. Okay. Now, we had that. Now we also want to increase the channel capacity. So we went to something called QAM, right? So QAM was always there in modems and all that, right? So what is there is you can modulate amplitude, you can modulate frequency, you can modulate phase. Okay, those are all analog communication. Now, what you can also do is you can take, instead of transmitting the bits, you start transmitting symbols. So basically, if I club 2 bits, right? So that makes a symbol. So now I have got 4 states. So if there are 2 bits, I have got 4 states or 4 bins. So I can decide what should be the amplitude of the carrier and what should be the phase. So that's your QPSK, right? And then they realize that if you do a very sudden transition in phase, the bandwidths are going to is going to increase. So to minimize bandwidth, they said, I'm going to use 2 QPSKs which are offset by 45 degrees. Then that became differential QPSK, DQPSK, right? After that, they said, okay, now let's see if I can bundle 4 bits together. So if I bundle 4 bits together, let me just skip to what this will look like. like here, for example. Okay, so what you see over here is QAM 16. Okay, so what this is this is a phasor representation. So let me just put here so that you can understand what I mean. So if I put one vector like this is Q, and then the another vector I put like this is I. Okay, so the center represents a 0 amplitude, right? And 0 phase. Phase is not defined at the center. Now each bin is basically 4 bits. So if there are 4 bits, there are 16 bins. And these bins are deciding what should be the amplitude and what should be the phase. So for example, this bin. Okay, so let's change the color. Okay, this bin and this bin. These two bins have same phase information, like they say same phase, right? But their amplitudes are different, right? Similarly, so basically each bin is unique. It has a unique amplitude and a phase. Now I can, instead of 16, I can also do 64. I can do 256. So when I do 16, I am clubbing 4 bits together. So that my symbol is 4 bits, right? My symbol is 4 bits. So I have 16 bins, and each bin is allocated to a different this thing. Okay. Now you use some kind of a gray encoding here. Why? Because in gray code, only 1 bit changes the state, right? Okay. So what they want to do is they want to minimize, they want to allocate the bins not just serially, like, you know, I start with 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. I don't go allocate these bins serially. I would rather look at the signal statistics, and accordingly I will allot the bins so that my peak to average ratio, which I will talk later, is minimized. So I have a smaller constraint on linearity. So we'll come to that. You just accept that these are not just allocated as is, but they are as per a certain algorithm to minimize PAPR, or what you call peak to average power ratio. Okay, so now this is, if I take this as a phasor representation, then there is, every bin has a unique amplitude and phase, which represents a certain symbol of 4 bits. So when I'm transmitting, I'm just transmitting that. Now there is a problem with this. The problem is phase information and amplitude information, they are way apart. Okay, so the best way to do this is take the polar representation of amplitude and angle, is split it up into 2 rectangular components. One would be called I component, which will be this one. One will be called Q component, this one. Now, if I'm jumping from one bin to another, I am basically jumping, I and Q are changing, right? So that's what a QAM is, okay? So basically we work with symbols, and we work with certain rectangular coordinates, which I call as I and Q. Now, if I want to send I and Q signals, usually I can modulate same frequency, because one I will modulate with the sinusoidal waveform, other I will take a cosine, because sine and cosine are orthogonal, right? So I can do a frequency reuse. I can send IQ on a single frequency. It's just that I will use sine wave and a cos wave for modulating the two. Okay, so that's what the basic of QAM system is. A QAM basically bundles up bits into symbols and allocates these symbols to different bins, which had a certain rectangular coordinate system as a I and Q. And so instead of one signal, I have got 2 signals which are orthogonal. One I modulate with a sine wave, other I modulate with the cos wave, I modulate it with that. So that's how I can reuse the frequency to send 2 sine and cos, basically two values, 2 signals I can send out. And when recovering, I will demodulate with one with sine, other with cos. They will not talk to each other because they are orthogonal, right? So that's the basic of QAM. So coming back here, what improvements did we see? We started going to higher and higher QAM. Okay, so if I take 6 bits, okay, so I have got 64, QAM 64. If I was to take 8 bits, I would have QAM 256. Now in 5G, you can go all the way from QPSK to QAM16 to QAM256. And what does it depend on? It really depends on the channel. Okay, there is always a fallback allowed. So if you are having a very high data rate and you realize that the bit error rate has gone up, you can fall back to, let's say, QAM64. If you still realize that your bit error rate is very high, you can fall back to QAM16. So it really depends on the channel. So the system basically can adjust. The PHY is supposed to support what you call the physical layer. Okay, is supposed to support up to QAM256 in 5G. So that's what that is. Okay, so now let's look at so we understood what is a QAM, and we understood why the data rate goes up. Okay, we understood what is OFDM and MIMO. We understood what is CDMA, right? There are two flavors of CDMA again. One is called frequency hop spectrum. So this is all basic classic you can find in any book. Direct sequences spectrum. So instead of that, there is going to be a chip signal, which is going to be used, which is going to be altogether. Sorry. Okay, so let's look at the basic radio. Okay. So basic radio is going to have digital processing, or what you called, all the compression, scrambling, error correction, block codes, turbo codes, or whatever you call that would be a digital processing. That is mostly done on some kind of a processor, right? So that's that. Now, when you go to PHY layer, I have to modulate, and I'm picking up some form of a QAM, right? So that I will call as a baseband. I'm generating a baseband IQ signal, right? So once I have generated baseband IQ signals, I will take I and modulate a sine, and Q modulate a cosine. And then I will combine them together or add them together, and then translate the entire frequency up to the carrier frequency. So that is the function of transceiver. Transceiver scales frequency. It either up converts frequency or down converts frequency, right? So that's the function of transceiver. Radio front end does the same thing with power scaling. You basically amplify the power before you launch it into the medium. Or when you receive it, you amplify the signal more strongly compared to noise, and then you basically detect it. So when you work with power scaling, you are talking about, let's see if there are other people who are in the lobby. Yeah. Okay. So the function of radio front end is power scaling. The function of transceiver is frequency scaling. The function of baseband processing is modulation, IQ modulation, right? So in a modern communication system, I'll do that. Now, in 5G, they also started doing sub-antenna systems, antenna subsystems. What it is, of course, they when you look at a wireless channel, it is a multipath channel. So you are receiving signals from multiple reflections. Okay, let's look at some questions here. Okay, can you please record how non-orthogonal FDM is better than orthogonal FDM? Okay, go and read from an author called Farhang. Okay, author is called Farhang. If you read his discussion, he has a chapter which basically discusses this. Okay, so the author is called Farhang. Okay, I can deal with this, but not outside the scope of this training. I can deal with 4G and 5G differences, and I can deal with the PHY layer, but I'll leave out for this workshop. If you, in future, I might do a specialized workshop on system view, where I will demonstrate the difference here on channel capacities. Okay, so this is right now, but my reference is the best author I have come across is Farhang, okay, from University of Utah. Okay, as per my understanding, you can accommodate more channels per spectrum in case of non-orthogonal, if that's the question. Yeah, I don't know if that is the question. Okay, how spectrum efficiency is improves in 5G communication. Okay. Okay. So it has a lot to do with the signal as well as noise. Okay. If you are looking at slow speed subcarriers, you are restricting to much narrower channel bandwidths. So your noise level has gone down right away. Okay, that's the first advantage you see here. Second thing is that your channels are orthogonal. So the subcarriers can be very close to each other, right? Because the information is, there will be overlap, there can be overlap, but because the information is uncorrelated, it really doesn't matter if you spill out a lot in subcarrier channels. So these subcarriers can come much closer, and the channel interference is not much of an issue because data wise they are orthogonal. So that's why the spectral efficiency goes up. You understand what I'm saying? It's because of the subcarriers. Okay, so basically you can do the maths, but I want to keep away maths from this workshop because I don't want people to be bogged down with mathematics, right? So I want to explain it the most simplified way I can explain that. Okay, so what happens is, in case of a multiple paths or multiple path communication, you receive multiple copies of same signal. Now, when you demodulate or detect that, okay, they are in different delays. Okay, you can equalize that. You can equalize delays and you can receive information. But then you cannot avoid something which is called fading. Okay, in a multipath channel model, you will come across. Okay, okay, I understand. You leave this with me. I will generate another workshop for this stuff. Okay, reason is it is going to be outside scope, and maybe all people are not interested in exact details, right? Okay, so I would come back to you with specialized, training on system view on this kind of stuff. So bear with me on for this workshop. I am going to be oversimplified here for the benefit of lots of people over here, right? And also the time constraint. So I would like to do this, but I would keep it to another workshop where I do a system view workshop on 5G. So I'll prove to you a lot of things over here in system view. But for now, the scope of this is very restricted right now. So please bear with me for this first workshop. The next workshop, I will come back with your, what your expectation is. Okay, so in a multipath, what's going to happen? Okay, you have to pick up a direction where you are getting the maximum signal to noise ratio. So to pick up, you have to orient your antenna beam. So beam forming system is, there is an antenna subsystem. You can point in a direction where you get the lowest bit error rate or lower or highest signal to noise ratio. And this you do using antenna subsystem, right? And that's why there is an antenna subsystem, which is an important part of 5G, right? This is also there in all kinds of radars, beam forming systems. So what we are going to develop here is we are going to develop here analog digital phase shifters and attenuators. So that's a part of this training that we are going to do a part of antenna subsystem, right? So that's there. So radio can be divided into, okay, radio can be divided into baseband digital processing, phi layer baseband processing, frequency translation, power translation, and beam forming. So this is what your basic radio would look like. Now, technologies involved, you should know a lot of FPGA stuff, right? You can do a lot of things using communication block set in MATLAB. You can do this in system view also, right? You can do a lot of stuff in that. You need a background in, little bit of background in FPGAs to do this kind of stuff, or even if you use processors, you can do that. Then you need some background in analog mixed signal. Okay, you need some background in RF CMOS passives and actives. As we go higher up in frequency, you need again high frequency concepts for same passives and actives. You need to know something about protocol stacks, right? Which is over DSP side. You need to know about something about channel modeling. So if you are going to do a modeling of a 5G system, you should know about the channel models, which we are going to use for urban and rural and all that. There are channel models built into system view. You can select any channel model for rural or urban or semi-rural or something like that, right? You can choose the channel model like, chi-square distribution or Nakagami or anything. You can do channel modeling there. You can do your own modeling there using a code, C code. Okay, so this is if you are a system designer, you might do it some point of time. System modeling and analysis, that's the major focus here for first 2 days. That's what we are going to do, and in the remaining days we will be focusing on this. So basically this portion and this portion is what we are going to focus on. Okay, and over here we will be building these blocks from modulation to your beam forming and steering. We will go up to there. Okay, so that's there. So right now it is 14:23. Okay, now we have a break coming at 2:30, right? So let's see the agenda side, because we have to stick to an agenda. This will be over here. Okay, so we are over here, but I want to discuss a lot of stuff on transmitter characteristics, power amplifier, front ends. Okay. 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 Anyways, I have colored this. Okay, doesn't matter. Okay, so 3 topics I want to cover. I have 5 minutes. Doesn't make sense, but let's talk about them. Sorry, where is my presentation? Okay, a basic system I would start with is I would have a IQ modulated IF. I'm going to put it into a variable gain amplifier. I will put a filter here, okay, a low pass filter here. I would take that and up convert it using IF to IF LO input to a mixer. I'll up convert to RF. I'll put it through a PA. I will have an image reject filter over here. Okay, so this would be the basic transmitter. Okay, and what would I be looking at? I would be looking at cascaded gains. I would be looking at gain compressions across the channel. Okay, I'd be looking at the output power. Okay, all these questions I would refrain from answering right now, because ours is a very basic workshop right now. I would do a separate workshop for this, right? So we will look at just what are the digital phase shifters, attenuators, how do you design them. We will not go into detail of this stuff. Okay, so for that I would do a separate workshop. Okay, can you please explain why a VGA in TX path is there? Okay, you have to have some kind of a variable gain somewhere in the channel, right? Because you are controlling what is the output power. So how do you control output power? There will be a power control loop. So I will basically sample in a power here, and then I will basically try to control this. So as I can decide what power level I should put out. For example, let's say I am going near to the base station, right? Then I need not transmit so much of power, right? So if I go away to the cell edge, okay, so I need a power control loop there, right? So I need some form of a gain control here to implement that, right? So that's why I have a VGA here. You will not, for analysis, you can throw it out. You can replace it with a fixed VGA here, fixed amplifier here. That's okay. But when you implement a power control loop, okay, you would need a VGA, right? So that's why I have just put a VGA just as a representative that this chain will allow you to scale the gain for a given power. Okay, so this is under a condition, right? So anyways, we have to look at the power level because we have to control signal to noise ratio at the receiver side, right? So I would have to implement a power control loop. So that's why this is there, right? So I hope, have I? Okay, fine. Okay, then I'll be looking at power rated efficiency. Why? Because mostly the handhelds are going to be depending on battery, right? So then I would be concerned about the efficiency of PAs and stuff like that. Then I would also be concerned about the cascaded linearity of this. So we are here concerned about two things. One is the interchannel interference. The other thing is the bit error rate, right? So we are concerned about two things over here. Okay, so that's where the linearity comes in. Of course, then there are different forms of transceivers. Okay, so basically you can have a direct conversion, okay, or you can have a low IF, or you can have a super heterodyne, right, where there is a IF, or you can have a dual conversion with two IFs. All has to do with how efficiently can you filter it. Okay, so it's all has to do with filtering. That's why you go from RF to IF. Your filters can have sharper edges, right? So a lot of things have to do with it. Now, when you go to direct conversion, there is other issue. The other issue is you have all your information is up after conversion. For example, this is up conversion, but in down conversion, after conversion, all the information is in the baseband, which is around DC. You cannot have any RF coupling using coupling caps. You have to be DC coupled. So all stages are DC coupled. Now, if the LO leaks into RF and comes back, mixes with itself, it gives a DC component which varies, right? So this can cause DC wandering, right? So all these mixer related issues come in, like, LO to RF feed through and all that stuff. Okay, so I'll look at that. And then the most important part is the stability, right? So this is what I will look at when I look at a transceiver. This is a baseline. This, what you are seeing, is a baseline. And what I'm going to discuss on this baseline are these. So this would be called some form of a budget analysis. So I'll be doing a budget analysis in ADS, right? So that's what I will be doing. Now, I assume that a lot of people understand a lot of stuff here, but just for sake of people who are fresh here. Okay, so what is expected from a transmitter? You will put out a certain power. And how do you decide the power? It is not just with the transmitter that you decide the power. There is a receiver also, which plays the role. So basically, if you start with a certain size of a cell, right, then you should look at what peak power a transmitter should be capable of. So that can be calculated as following. You can have sensitivity of the receiver, which is the minimum signal strength for which a receiver can do a faithful demodulation. A faithful demodulation means a certain bit error rate. Okay, so that's minimum signal strength is called sensitivity of a receiver. Add to that the attenuation. This attenuation basically is, if you have a water absorption band, then water is going to absorb a lot of stuff. If you have oxygen absorption band, then oxygen is going to absorb. So this attenuation is basically some form of a absorption. Okay, then there are antenna gains there. So if your transmitter receiver are isotropic, then basically you are seeing directly the path loss, which is going to be R square. Is the power will be dropping with 1 over R square. Because if you assume a bulb, for example, which gives out light, so at a distance R, the power density goes down by 4 pi R square. So you take the transmitted power divided by 4 pi R square, that is going to give you power density. And then you multiply with the antenna aperture, that much power you are going to collect. Okay, so that 1 by 4 pi R square, that is called the path loss. Okay, so anything which is a point source where the power will decline by 1 over 4 pi R square. If it is a line source, it will go lower than 2, lower than r square. Okay, if it is a square, for example, if it's a square radiator, right? So at a very large distance, it will be a point source. But for the distance of my concern, it would be much smaller than 1 over r square. Okay, so the path loss basically depends on your radiator, right? So basically, if I was to take a point source, then power will decline by 1.4 pi r square. Okay, if I take a line source, it will be smaller. If I take a square source, it will be smaller, right? So that is referred to as path loss. And to that, I would add the antenna gain. So I'm calling it loss, but this is an antenna gain. Okay, so I have a transmit antenna gain, a receive antenna gain, okay, which I'll add up. Okay, and then the attenuation, then the sensitivity, all this has to be provided as a peak power by the transmitter. So transmitter should be capable of handling a receiver which is at the edge of the cell also. So that's how you compute your peak output power for a system. Okay, now talking of certain systems like GSM is 2.5 watts or 3 watts. CDMA is going to be half watt or quarter watt. Okay, if you go to Wi-Fi, we are talking about something like 19 dBm or 20 dBm, 21 dBm linear, right? So depends on system to system. They have been designed for certain, range and stuff like that, right? Again, it's a function of wavelength, right? So if you have, okay, so it comes in denominator lambda here. Okay, so if you have a higher frequency, it's going to have a larger path loss versus a lower frequency. So it depends on that also. My formulas may be in error on science somewhere, so bear with me. In the books, you will be able to correct it. Okay, so output power is the first thing which I am expecting from a transmitter, right? And then I have two bandwidths I have concerned about. One is the system bandwidth, other is the channel bandwidth. Channel bandwidth, I'm concerned about the noise, signal to noise ratio and all that. System bandwidth, I'm worried about the interchannel interference and about the channel capacity. Okay, so that two bandwidths come into picture. So if I design for a certain system bandwidth, okay, so the analysis for signal to noise ratio, you will start with certain channel bandwidth, not system bandwidth. Okay, so that's there. So bandwidth is one more concern. Linearity is a concern because if you are going to use some form of modulation like, QAM 16, 64 to 56, then the bit error rate is directly related to that. Okay, so in linearity, you can have something which is spilled from the adjacent channel. The baseband is totally uncorrelated. So you call this intermodulation distortion. Now, if you are having the bandwidths which are correlated, like, the interference which is correlated, then I would call this as in modulation or AM, PM conversion. So I'm going to discuss that, right? So all these are going to affect the bit error rate. Okay, so signal strength and noise doesn't go independent. It is signal to noise ratio. But then when it comes to signal, you are talking about a certain throughput rate and you're talking about certain linearity. So interchannel interference is a different issue. AM, PM conversion is an in modulation issue where the basebands, or rather the basebands around the carriers, they are correlated. So we will discuss what is in modulation, okay, or intermodulation. Okay, so linearity becomes important from that point of view. Spurs basically are related to stability mostly, or leakage components, again directly contributing to the noise, right? So you might not just have the thermal noise, which your classic sensitivity calculation uses. It may be a noisy environment. Okay, you might pick up spurs from other systems, which may be blockers also. So you might pick up blockers, which basically is an IF issue also, choice of IF, right? So blockers are issues here. Now, if it is a frequency hop spectrum, then that's not much of a issue here, right? Because their frequency is hopping anyway, right? So that's there. Blocker is still an issue. Okay. even if you are not at the image frequency. So we will detail this as we go ahead. Stability. So basically, stability is a must thing on a transmitter. Okay, so these are the basic things which you should look at. There may be much more things to look at. Okay, there may be many more things to look at. Okay, but for now, for basic to get started, we will put together a system and we will look at these stuff. Now, little bit of, so let's say it is 2:30. Okay, so I'm not going to go on. I'm going to give you a break. Okay, so what I want you to do is just look at these 5 slides which I have discussed, right? Don't go beyond that. Let's take a 20 minutes break, right? And then I will explain you something on PAs and linearities and some things which will come across the entire chain. And after that, we will directly go into using behavioral level models. So basically, I'm expecting to cover concepts first before I start dealing with putting these behavioral level models. So the whole flow goes like this. I will do the entire transmit receive chain using models. And I will also discuss the restrictions of a model because the models are not perfect, right? Then I will replace these models. So if I go forward, let's say the third day, I will start replacing these components with the CMOS components and still do the same analysis, right? So basically, if you browse through, you will come across somewhere up to here. So I will discuss how do you generate these, okay? How do you set up a Ptolemy bench to generate QAM 16 or 64 or 256 signal, right? So I will discuss that. And after that, I will go into a process and I'll start making these blocks, starting with LNA, PA. I will not cover switch. I'll cover switch, but from a different perspective. And then I will do what is called digital phase shifters and attenuators. Okay, 5-bit, 6-bit. Then I will do, I will start putting the chain, transmit and receive chain. I'll do the mixers, VCOs, and I'll start putting the chain together. So this is like, receive chain, right? So I will start with the system level and I will go down to the transistor level. So this is all going to be transistor level. And we are going to use GPDK. If you want, you can use any process. The thing would work. Okay, how can you get the PPT? You go to my LinkedIn account and you look under activities. You will come across this PPT and you click it and it'll open full window. And then on the right top, you'll see download button. Okay. At the end of the day, I will do all the recording of the sessions. Okay. Okay, welcome everyone back. Okay, there's a question on people want GPDK. I would give it to you, but let me add a word of caution. The word of caution is the following: only in the PDK, only NMOS 1 and PMOS 1 are modified. So basically, all other models which are using other bins, in the sense not other bins, other models. So for example, if I go here, let's open this one. Okay, let's just cancel this. Okay, let's look at the models, right? Not here, sorry, close workspace, practice. Okay, let's look at a particular okay, let's just look at this one. Okay, so this GPDK is not so good. It has, you see, there are lots of transistors here, NMOS RF and HV high voltage, NMOS 3, NMOS 3 HV, and all that. Okay, all I have modified is NMOS. Okay, so if this NMOS, I have modified only this one. So for example, okay, you find a model where I cannot do this. Okay, it comes up with a warning. That means that that is not modified. So basically I have modified the first one, not any other ones. Okay, so for example, let's pick a high voltage one. Okay, let's try to change this to 130 unless, okay, it works. But the thing is, I have validated model only for NMOS and for PMOS. And these two models I have touched. Other than that, whatever is available from Keysight, that is very crappy here because this is a very old library. This is not even done by Keysight. This is basically translated and generated by Cadence guys. Okay, so right now you will not be happy using any of the stuff other than NMOS and PMOS. And then resistors, only two resistors I am confident with, which is poly high res and poly res, and then MRes. Okay, other than that, I haven't validated this inductor model. I haven't validated the capacitor model. I haven't even touched them. I have done various simulation on bipolars, but I'm not happy with them because I cannot even simply generate a Gamal plot for this NPN. It was totally absurd Gamal plot. Okay, so what I'm saying is I can share this PDK, but expect to use only NMOS, PMOS, and inductor, capacitor, and resistor. Don't use varactors because these varactors are very crappy, very bad. Okay, so what I'm saying to you is, I will share this PDK, but I have only worked with NMOS, PMOS, inductor capacitors, and these resistors. Okay, other than that, I haven't touched any models. So whatever is there, like for example, this using this transistor as a what you call as a varactor, I haven't. I have used that. I have found it very crappy. Rather, just use a transistor and do the connection, and that's it. So what I'm going to share is a PDK where you can use only NMOS, PMOS, and inductor capacitors and resistors. Other than that, I haven't touched any of this stuff. So this PDK is not going to be good for that. So it is only for your proving your concepts to yourself and doing some kind of initial study. But I would recommend that you sign up with the Foundry and get their ADS PDK. For example, IHP will give you a ADS PDK, and then TowerJazz will give you a PDK. So this is there because I don't have a permission to use theirs. So I had to modify this demo PDK, and you can use that. So that's the limitation. So I am going to send this as a link. Okay, so let's close this. Okay, so I have done a zip. I will put it on my Google Drive, and then I will share a link so you can get it down from my Google Drive. Okay, so for now, we are not going to use that, but at the end of the day, I'll do this, and you will be able to download it. Okay, so let's proceed. Okay, okay, so let's come back to here. Okay, gain in a chain, I have various gains and losses. Okay, negative ones are losses, positive ones are gain, right? But what I want to tell you is that we have power gain, available gain, and transducer gain. Now, what is available gain? If you do a conjugate matching on input output, then the gain that you get is a maximum gain. So that maximum gain is the available gain. Okay, so with the conjugate matching, okay, you have available gain. Same thing is true for LNA. For example, if I tune the LNA for gain, then I'm looking at available gain or G max. Now, when I tune for noise figure for a LNA, then I would not have an available gain. Now, it depends on where I'm allowed to put a mismatch, right? So for example, for PA, I might tune the output for linearity, okay, or for efficiency, right? In that case, the available gain is the maximum gain, but I am going to talk about power gain. In power gain, the mismatch at the input and the mismatch at the output, both are inclusive in here. Okay, so it is a power gain, P out versus P in. While available gain is P out dash versus P in dash. Okay, so this I'm assuming that it is conjugately matched on both sides, then that will be available gain. Transducer gain is P out as is, and P in is matched as P in dash, or P in is matched conjugate. Usually in PA designs, your input is conjugately matched for gain, right? It's conjugately matched for maximum power transfer. So transducer gain is what makes sense for a PA, and that will be same as the power gain, because on the inputs usually your inputs are usually matched to 50 ohm as a conjugate match here. They're matched to 50. So in that case, this transducer gain and power gain is the same thing. Okay, so is there a question? Okay. So we have power gain, which includes mismatch on both sides. We have available gain, which assumes conjugately matched on both sides. And then we have a transducer gain, which assumes that you are conjugately matched only on the input side. Output side, you are going to do as per your requirement, right? So there are three gains. Mostly we deal with power gain. Okay, so I have said that. Next thing is cascaded. Next thing is a role of a power amplifier, for example. Okay, so well, it's an entire chain on the bottom, and then it is going to receive. So what is the signal going through? The signal is going through all kinds of losses. So first of all is the path loss. Second is the attenuation. Third is the fading. Well, the fading in multipath case, if they are mobile, fading. Fourth is how much noise am I picking up in this? So I'm concerned not only about the signal received here, I'm concerned about signal related to the noise which is received here. So a PA has to put out that much of power so as to assure a certain signal to noise ratio at the antenna. Okay, so that all this figure is about. This figure is just saying that this is my signal is going to degrade because of path loss, attenuation, fading, and then it is going to pick up noise. But I have to assure a certain signal to noise ratio here at the antenna. So my signal output should be strong enough for a minimum signal to noise ratio or sensitivity of the receiver. So that's all this cartoon figure is about. Now, when I put a PA in FDD or TDD system, okay, there are different expectations from a PA. Okay. So let's say if I have a TDD system, time division duplex system, I'm going to have a TR switch here. In case of FDD system, I'm going to have a circulator here. So what does it mean for a designer, PA designer, for example, right? So here the PA is operated in pulse mode. right? So once I'm transmitting, I have a PA on. If I am receiving, I have a PA off, because I have to guarantee that the noise received in this channel is, because they are the same frequencies, right? So the noise received is going to be less. Okay, so I would turn off the PA, the transmit chain here. The PA I would turn off here. Okay, so it is operated switched here. That means that the junction temperatures are going to be lower, right? That also means that there is going to be a droop in gain and other parameters when I turn on the PA, because the junction temperatures are going to rise. So all this has to take place while you are transmitting a preamble. So if it's a short or a long preamble, in that time period, this PA has to thermally stabilize, right? So the gain droop is compensated for. Okay, so this is what happens in TDD system. In FDD system, it's like PA, LNA are in different frequency bands. And then the concern is how much PA noise is put out on the receive band, right? So that's the concern. Okay, so over here, isolation is also a concern here. How much PA is going to put into LNA, right? Because there is a circulator here, PA is on all the time, right? So that restriction is there. Next thing is the ruggedness, okay, Viswar. Now it depends on the switch, right? So if I'm using a switch, I'm going to see all kinds of switching transients. Okay. Okay, I will answer your question on this in the next slide. Okay, I've just talked about gain. I've just talked about a P out. Now I'm talking about PA in TDD and FDD system. I will come back to the power added efficiency a little later. So bear with me for that. Okay, so now if I use a circulator and the antenna sees a mismatch, so I have this circulator which is protecting my PA. Okay, so the PA is not going to see a lot of viswar, okay, or a mismatch. Okay, the antenna basically has a circulator in between, which is 50 ohm here. So the viswar seen by PA is much smaller as compared to a TDD system. Now in TDD system, this switch can be a absorptive switch. So even if it is off, it is terminated into 50 ohm. But the problem is the transition. So when you are transiting from transmit to receive mode, okay, there is a period in which there are transients. Okay, there it becomes important that the PA should be rugged. Second thing is PA is directly connected to the antenna. So if the antenna is going to see a mismatch, then the only thing which is protecting here would be a filter. Actually, there would be a filter here in both cases. The only thing that is protecting it is a filter, but filter doesn't do much. Okay, so the PA is going to see a lot of ruggedness issues. It has to tolerate a very high viswar. Okay, 8 or 9:1, or maybe people go up to a non-destructive case up to 20:1 viswar. Okay, performance is like 2:1. Okay, so you have to guarantee a performance on 2:1 viswar, for example. Okay, and a ruggedness up to like 20:1 viswar, hot and cold cycles and stuff like that. So if you want to design a PA for TDD system, the PA has to be rugged. Okay, and if you want to design it for CW system, then the PA ruggedness constraints are little relaxed, right? So that's the difference between if you design a PA for TDD system or a FDD system. That basic difference would come in. Second thing is the settling time. Okay, in TDD system, you are going to switch off the PA. So basically, when you switch it on, it has to thermally settle as well as electrically settle. Now, to have a very good electrically settling time, all your bypass caps are supposed to be smaller. Now the next comes is the linearity issue on bypass caps. Okay, so it really depends on the mixing and basically the how the match is in a Smith chart. Okay, so bypass caps are supposed to be smaller on a TDD system PA, while the bypass caps can be larger on a FDD system, right? So there is a settling time involved in TDD system, which is not there in this. Okay, so this is a basic difference between the two when you design. Okay. Now, at a glance, I will tell you there are different topologies possible. Okay, you can have a non-switching amplifier, which is usually done for linear applications. You can have a class A, B, or C, or maybe a push-pull configuration of B or AB. these are all linear. And the distinction is the conduction cycle, how many degrees of conduction cycle is there. So if, for example, you have a class A, then you are going to swing on this transfer function, or what you call the output characteristics, not transfer. Output characteristics, you will see the entire swing of voltage and current if it's a class A. Then you bias it down, it will become class AB, and then class B, and then class C. Okay, so here the transistor is still acting as a voltage controlled current source, right? Now, if you hit it with power, then the self-biasing will cause this loop to balloon out into a rectangle. So you can plot that also and see. But to a certain extent, you will still see this kind of curves. Okay, under transfer function, you can, not transfer, sorry, under output characteristics. Okay, so this is what happens with the linear amplifier. If the conduction angle is 360 degrees, then this is going to have an excursion in the entire saturation region. And what it means is that there is a voltage and current in the device simultaneously. So there is a power loss here. So the efficiency is going to be the lowest. Okay, so for a class A, ideally the efficiency will be 25%. If you couple it with a transformer, it will be 50%. If you go to class B, it will be pi by 4 or 78.4%. Okay, if you go to class AB, it will be somewhere in between them. Okay, and then class C, now it depends on how much power you want to put out. You can keep biasing it lower and lower, and the conduction angle will keep reducing less than 180. So let's say at 120, okay, at 120, it will be almost as good as your, better than actually class B, but it will be in 90s if you want. Ideally, it will be 90s. Okay, so that's the efficiency with class C. But the problem here is you will not be able to put out power because you are cutting down the conduction angle, right? So this is what a non-switching amplifier or a linear amplifier is going to be, where the device is a voltage controlled current source. In switching amplifiers, the device is a switch. Okay, so what do you mean by switch? Voltage and current are orthogonal, which means if there is a voltage, there will be no current. Because when the switch is off, there is no current, only voltage across the switch. When the switch is on, then there is no voltage across it, only current. If I assume the resistance of the switch is 0, then basically ideally switch would have voltage and current orthogonal, right? So the major chunk of the loss is gone. Okay, so you are basically going to swing along this axis or along that axis. So either there will be current, no voltage, or there will be a voltage, no current. So if I design a class E and plot these waveforms, they will be swinging along these two axes. So I will design a class E and show you that how it swings. Okay, now that's a switching amplifier. Now another form of switching amplifier is a class F amplifier. Now what is class F? Okay, now what happens is if you look at a transistor, if you pick up a big transistor, parasitics are going to be more, like, the output capacitance is going to be more, the Miller capacitance is going to be more, right? And then the lead inductances would be there. So the higher, and then there will be losses also in terms of extrinsic resistances and all that, right? So as the transistor becomes bigger and bigger, okay, its parasitics become higher and higher. Now the active power which you can deliver, okay, goes on reducing. Okay, so it is advisable to use a small transistor to put out power. Now, the restriction of a small transistor is it has got Vmax and Imax. So Vmax into Imax would be the power capability of a transistor. So if I take a topology and find out what is the maximum power I can deliver and divide it by the Pmax of a device, that will be called device utilization factor. So now I can compare various topologies for a given device utilization factor. So now what is a class F amplifier? What it does is it flattens the voltage waveform across the output of the device. How it does it? It is going to peak, well, it is going to basically short out all the even harmonics. So that means that the sinusoidal waveform flattens out. So that is called maximally flat class F. So their class F has got three divisions again, F1, F2, F3. Okay, so all of them ideally are 100%. How they do 100% efficiency? The voltage across the device and current through the device, they are out of phase. Okay, because of that, there is no dissipation in the device. Next is, what is the source of loss? That is the reactive power, or the power which is stored in the parasitics. For example, output capacitance, or let's say the lead inductance. Okay, so you have a charge on the output capacitance. So as soon as you turn on the switch, that charge is going to go to the ground, right? So that basically is the cause of the loss. Okay, so class F amplifier basically has a 100% efficiency. It's a maximally flat class F. All the even harmonics are shorted out at the output. All the odd harmonics are opened so that they can go to the load. And class E basically is a different amplifier. So let me go back to start writing stuff so that I can explain you better. Just 1 second. Concepts. Just 1 second. Space the server. And here I am going to put space text viewer. Okay, let's connect here. And it's connected. Let me start writing stuff. Hang on a second. Okay, people can see this, right? So let me say this. There is a switch here. So this is my equivalent of a transistor. And then what I do is, okay, at this, sorry. At this, I'm going to do a match here. And then there is a load. Right? And then there is a choke here. And there is a supply here. Okay? And this is my match. Okay? So now, if I short out all the even harmonics, then what's going to happen is, let's say this is a sine wave. Okay? And I have voltage across the device, then current is not there, or current across the, so if my switch is off, then basically the entire voltage is over here. And if the switch is on, like this, then only current is there, voltages are ideally zero, correct? So I have voltage and current, which are in quadrature. Okay, voltage and current, sorry. Just bear with me on the color. Okay. Oh no, I'm at the wrong place. So let's say I have a voltage waveform here. So the current waveform is 0. And then let me change the color. Then I have a current waveform. Voltage is 0. Okay, voltage is 0 over here. Okay, so if I guarantee a quadrature like this, okay, if I guarantee a quadrature like this, then the loss in the switch is 0. Loss is equal to 0 in the switch. Now, what's going to happen is that, let's say there is a parasitic capacitance here. So let's just delete this. There is a parasitic capacitance here, and then there is a switch here. Okay, This is the output capacitance of the transistor. Okay. So now what can happen is, let's say I have a charge buildup on this capacitor, and as soon as I turn this on, this charge discharges this way. So I'm going to see a loss of all the charge which was stored here. I'm going to see a loss here. So basically parasitics, and let's say that there is a lead inductance also here. Okay, so if there is a lead inductance and capacitance here, okay, all the magnetic energy is stored in the inductor, lead inductance, and then all the electric energy is stored in the shunt capacitor. Now, if I switch on and off this switch, okay, the energy is going to ground to the ground, and I'm going to lose the efficiency. So what are the sources of losses? Okay, in a power amplifier, what are the sources of losses? Okay, first is going to be the switch loss. Okay, so if there is a voltage, there should not be a current. If there is a current, there should not be a voltage. If that is so, then the switch loss will go to 0. If they are in quadrature, if V and I in quadrature. Okay. Now, the next thing is, when I switch on, okay, I am going to ground, okay, the charge stored in the parasitics. So basically the energy stored in parasitics. So the other cause of loss is the energy stored in parasitics. Okay, so I have to be careful about when I switch them on and off. Okay, so when we come to class E topology, I'll show you what happens. Okay, so that's the other loss. Okay, so the energy stored in parasitics can be grounded. Okay, other than that, okay, there will be a conduction losses because of the resistances. Or conductor losses, I would say, not conduction losses. Conductor losses due to resistance. And then the fourth one will be radiation losses. And if you want to refer to a paper, look for class E implementation by Frederick H. Raab. Frederick H. Raab. Okay, so he will discuss the sources of losses in a power amplifier. Okay, also there is a paper by Nathan Osokal on class E. Nathan O. Sokal, 1975. Okay, so you'll find these two papers. They will discuss about various losses and how to minimize them. Okay, so we have seen that there are amplifier topologies which are switching amplifiers. You have got class F. So what is class F doing? Maximally flat. So if you use a small transistor and flatten the voltage waveform, so for a given power capability of a transistor, you will be able to put out more power from a given topology, right? From this topology. So the device utilization factor here is 1.59 for class F. Device utilization factor is 1.59. For class E, the device utilization factor is 0.0981 ideally. And for class C at 120-degree conduction angle, you will see the same. Device utilization factor is the ratio of what is the maximum power you can put out from a topology to the maximum power a device can handle. Okay, so class E amplifiers, it is going to be 9.8%. While for class F amplifiers, it is 15.9%. Class D is basically a push-pull class F. So basically you can take 1.59 and double it. So that is going to be 3.18 roughly, right? So class D, which is like a push-pull class F, which is going to do a very high device utilization factor, right? So that's various switching amplifiers. All these switching amplifiers ideally can give you efficiency of 100%, right? This is because you are going to minimize all these losses, Okay, so you are going to minimize all these losses. Okay, now how easy is it to design one of these, and where are they used? Okay, now if you want to do any system where there is a information in the envelope, so what are these systems? The QAM systems, right? So in that case, I would have to do a class AB or a class A kind of amplifier. So my efficiencies are not going to be very good. Okay, we'll be like the best achieve will be like 40, 42, 43%. Okay, not more than that. And as you bias them down, you will have linearity issues coming up. We will discuss that. Okay, so people are waiting in the room. Okay, I'm really sorry, admit all. How about inverse class E? Can we use TWA type of amplifier? What is the power added efficiency? Yeah, I'm going to answer these questions. Okay. Okay, so I will cover class E and inverse class E. So just wait for a second. Let me explain the differences first. Okay, so now if you have information in the envelope, you can't do much about this. Now, let's say if you are like a QPSK system or a DQPSK system where the amplitude is fixed, all the information is in the phase. In that case, you can use a class E or F amplifier or any of the switching amplifiers, because all the information is in the phase. Okay, so that's the story there. Okay, so now let's assume that we are going to design a class E amplifier. Okay, first let's understand what is happening with class E. Now, we are in a 5G system, we won't use that, but for the comprehensive nature, I would like to, and also I want you to think about it. Okay, so let's say there is a supply, and then there is this choke, which converts this voltage source into a current source. So let me just switch on. Where is this? Yeah, Aparna, can you turn off your? This thing? Yeah, fine. Okay, so next thing is I am going to put here a switch and a shunt capacitor, and then I'm going to put this and this and a load. Let's say this is R, this is CS, this is LS, this is CSH, and then this is a choke, and this current is IDC. Okay, now let's do like this, that let's assume that there is a sinusoidal output at R, right? So basically what is happening is I am going to chop the DC, okay, generate some kind of a AC, right? That's what is happening over here. I'm chopping the DC and generating some kind of a voltage and current, which is changing with time, right? So I'm generating certain frequency, which is going to be the switching frequency F0. Okay, I'm switching this at F0. Okay, so now what's going to happen is, let's assume that this is a sine wave here. Okay, sine wave. Now, this is sine wave current as well as sine wave voltage. So let's look at the sine wave current. So what flows in here is going to be the difference of the two. So if this is I load is a sine wave. Sorry. Okay, I load is a sine wave. And then the input is DC. Then the output is going to be, well, what flows through this capacitor switch combination is going to be a DC shifted sine wave. So let's make a DC shifted sine wave. So this is a DC shifted sine wave, right? Now, this DC level has shifted up. Sorry. So basically, is DC level is over here. So this DC level has been shifted up. Okay. Now what am I going to do? I am going to choose 2 points on this waveform. Okay. Let's say one point is over here, and 1 point. So rather 1 point I'll choose here. Okay, such that this area and this area is going to be canceling out each other. So the net area under the curve equal to 0. Okay, so now if this is a current, okay, then the integration 1 over C integral I dt going from I1, or rather going from T1 to T2. Sorry, going from T1, okay, so T1 to T2. That is going to be the voltage across this capacitor. Okay, so if I choose a point T1 such that the net area under the curve is 0. So that means that when I turn on my switch over here, that means that the voltage over here is 0. So at this point, so let's say at where? At T2. Come on. At T2, my voltage is 0 across the capacitor. And if you see the current waveform, the current is also 0, right? So I have a 0 voltage and 0 current. 0 voltage across I have a 0 voltage across the capacitor. And what about the current? In the parallel combination, the current has also decayed to 0. That means when I'm switching on the switch, the capacitor is storing nothing on it. So when the capacitor is storing nothing, then that loss which you are going to face because of energy stored in parasitics, that loss will be gone. Okay, so that means that the switching is smooth. Okay, so now the net voltage will be the integration of this curve, which is shaded, is going to be like this. Correct? So this will be the voltage across the switch capacitor combination, right? And the switch is open. So the current through the switch is 0. But this piece of the sine wave which is shaded is moving through the capacitor, which causing the voltage, right? So the voltage across the switch is maximum, but the current through the switch is 0. Most of the entire current, this piece of sine wave which is shaded, is going through the capacitor. When this happens, the net power dissipated in the switch is 0, right? Because there is no current in the switch, but there is a voltage across the switch. Now at the turn on, this voltage is 0 as well as the current is 0, right? That means that there was nothing stored on the capacitor. Okay, so when the switch is turned on, the remaining of the cycle, which is basically this, the remaining of the cycle is passing through the switch. Now, if the resistance of the switch is 0, then the voltage across the switch is 0. So now you have a quadrature between the current and the voltage, and the net dissipation in the switch is 0. Secondly, when the capacitor is turned on, when the switch is turned on, the capacitor was storing 0 because there was no voltage, no current. So at that time, the loss of energy stored in parasitic would be 0 because nothing was stored on the parasitic. Okay, so I have generated voltage and currents in quadrature. Now, if I filter this waveform out, so this voltage waveform, if I was to filter out using LSCS, I would let only sinusoidal through. Okay, so what is happening is this combination traps entire current harmonics. This combination traps entire voltage harmonics. And what you get here is pure sine. And the sine, of course, this is a resistor, right? So voltage and currents are going to be in phase here, while they are going to be quadrature in the switch. So that's how the efficiency of 100% would be guaranteed. Okay, so this is how a class E works, and its efficiency is 100%. Now, I can show you a design of a class E, but this is beyond the scope, okay, of this workshop, but I would show you. It's very easy to do that. Okay, so let's see as a diversion. Let's see as a diversion. Not here. Backup.net, no. Under projects, is there a project folder? Trainings, system view, software, PowerPoints, outward, bookshelf, backup. It has to be under backup. C#, no, these are all books. Are there projects here? Company.net, digital design. Just bear with me a minute. MATLAB. Come on. Just bear with me a second. I'll just find it out. PPT backup. Just 1 second. Okay, I have it on a different machine. What happened? Okay, let me just change one more thing, because this is not the resolution I want to work with. Come on, guys, so slow. Okay, this is what I have written earlier. And how does it solve this problem? Okay, how does this solve this problem of designing these? Okay, how does it solve this problem? Okay, so the way to solve this design is switch off and switch on. Okay, switch off and switch on. You write two equations. Okay, two equations in Laplace domain. And then you solve them in Laplace domain and come back to the time domain. Okay, so you will get two simultaneous equations, one for switch on and one for switch off. And in one case, when you have switch on, C shunt will be shorted out. Okay, and when you have switch off, C shunt would be the part of this Kirchhoff loop. So there are two loops and two equations. Okay, and if you want to refer to, there is a paper on these two equations, which I should have here. I will give you a reference to that paper. So they know they tell you how to solve this. Okay, and based on that, I have this thing. So let's design for 10 ohms, for example. Let's say a duty cycle is, let's say, going to be 50%. And let's say the quality factor is roughly around like maybe like 10 or 12. Okay, so let's put a 8 quality factor. And let's say we are going to design it for, let's say, 5 gigahertz, right? And let's say a supply voltage of, let's say, going to be like 3 volts. And let's say calculate. So this is the value. Now, these are going to be the waveforms. Now the question comes is, how is it going to look in ADS? So let's put together a simulation for class E. Class E. Now, there was a question on inverse class E. Okay, it's just that the voltage and currents are there's. Okay, I am not thinking of giving you out this software, but let me see. Okay, now let's just first validate this. Okay, so I'm going to create a workspace, and I'm not going to worry about any stuff. I would say just want to use a standard this and finish. So I've created a blank workspace. I'm going to create a new schematic. Okay, and I will call this as a class E. Class E. Okay. Now, what I'm going to do is this. I am going to pick up lump components, right? So I have a L, which is around 2.546. Okay, so I have a L of 2.546. 2.546. And then I have a C of 0.469. C of 0.469. 0.469. Correct? And then I have R of 10 ohms. Okay, now 10 ohms can be transformed, use a quarter wave line to 50 ohm or any impedance you like. So I'm not going to worry about this resistance for now. Okay, and here, this, and I have a choke where I'm going to use DC feed as a choke. Sorry, DC feed as a choke. Right, and I'm going to put 3 volts across it. So I'm going to go to sources, frequency domain, and put a 3 volt here, like this, 3 volts, right? And then I'm going to take a static switch. Really, you don't need a very good model for a switch. Okay, and I'm going to take a static switch, which is from system switching, right? System signal system switch algorithmatic, and this is the switch I'm going to use. Very simple switch, and I'm going to put this switch over here. Okay, so this is my ideal switch. I'm going to remove the model because it is expecting a model. So I'm going to say that when voltage is above, so when voltage is, so this V1 I'm going to put as 0.08, and this is going to be 0.1. So basically, as soon as I have a positive waveform, I am going to have this on, and when it is on, it is going to be like, let's say 1 milliohm, and when it is off, it is 1 mega ohm. Okay, so this is my ideal switch here, and this goes here, and I'm going to put a shunt capacitance of 0.639. So this includes the output capacitance of the transistor. So if you want to design for a given frequency, make sure that the output capacitance of the transistor is smaller than this. Otherwise, you will not be able to design. Okay, so I'm going to put here 0.639. 0.639, right? And there you go, it, and you put here. Now, here I'm going to give a sine wave. Okay, let's say this is going to be any frequency domain source. Frequency domain, let's put a P1 tone. Doesn't matter. Let's put here, let's say 8 dBm or 10 dBm. Doesn't matter. And this design is at 5 gigahertz, correct? Okay, so 5 gigahertz input. Okay. Now, I can do on this harmonic balance, right? So let's go to simulation HB and put here. Now, if this is going to be 5, I can use 5 order. So let's put a big order number here. Let's say 29. Okay, so my switch is ready. I want to see the voltage and current here. So I'm going to name this node and this node. So this node, and I'm going to put here the total current drawn. So the total current drawn would be into this combination. So I want to see the total current drawn here, and I want to see the total current drawn here. Right, so I am going to probe components, and this one I'm going to rotate, put it over here, and this one over here, and let's rotate this one over here. So this one is IO, so I out, and this one will be ICSH, and this one is going to be ISW, and this I will name as VC. This I will name as VC is the node voltage, VC. And this I will name as VO or V out. Correct? So this topology is same as this topology. Correct? I'm expecting this waveform. Okay, so let's do this. So now I'm going to simulate this harmonic balance. It's already harmonic balance in here. I'm going to hit simulate. Okay, so I'm going to first plot VC. And I want to look at the time domain signal. So that's your class E. That basically looks like your ideal class E, like this. So this is your class E, right? And this voltage goes up to 10 volts. So this voltage goes up to 10 volts. So you can validate here, plus you can validate here. So this red waveform is your voltage across the switch. And this is your harmonic balance output, right? Now let's put the current in the switch. Time domain signal. That's your, I'll put it on a different axis. Let's put it on a right axis. Okay, so this is your class E current waveform through the switch. This is your class E current waveform. Now, what you see here is a harmonic balance anomaly. It is nothing to do with your class E design. So if you go here and increase this to 129, that thing should go away. So there it is. So basically what you are seeing here is that. Okay, so that's not there. Now let's see what is through the capacitor. Okay, this is through the capacitor. Let's put it on the right axis and let's give it a green color. Okay, so that's your sine wave. A piece of sine wave which is blue colored flows through the switch, and a piece of sine wave which is green colored flows through the capacitor. This switch, the waveform which flows across the capacitor causes this voltage across the switch capacitor combination, which is filtered to the output based on a certain Q. Okay, it is filtered to the output to give V out and I out. V out and I out. Okay, so basically this is your V out and I out, and let's put this on the right hand side axis. Okay, that's there. Now, if you want to look at the spectral distribution of VC, the spectral distribution of VC. Okay, so there it is. So at fundamental is going to be that output. Okay, 23 is over here. Okay, so let's look at the power spectrum here. So in my workshop, in my this thing. Okay, so here there is a mistake in my software, but I'll show you. Let me show you that. Okay, so here kind of I messed up with the sign, but this is going to be 23 dBm. Okay, so this is 23 dBm, this is 23 dBm harmonic balance. And this is going to be 17 dB down. Should be 17 dBm down, right? No, the third harmonic is going to be that. So basically, this is because of the Q. How many harmonics am I putting? So I can design for a different Q, and I can change this thing. Now this software can design for any Q and any slope actually. So I can allow some slope here. Sorry, I can allow some slope here, and then you will see a current spike here because you are allowing the certain voltage across, right? So, or rather certain current or charge stored in the capacitor. So it will come up as a spike here. So that will be suboptimum class E. Okay. So this class E, you can always change the topology to reverse voltage and currents. Okay. So in that case, it becomes a inverted class E. Okay. So you can see that this is nothing but solving certain equations. So if you want to see the equations, sorry, let me open again. Let me open again. Space test view. Okay. So now if you want to see the equations for this software, instead of exe, I would have to open this in C#. As it will not open as a, oh, source code is where? What happened to my source code? Application extension program debug. This is a program debug, but this should be a source code here. No, I'll find out the source code. But what it is doing is it is solving two equations. That's all it is doing. It is solving two equations which I talked about, right? So let's keep this apart. Let's keep this down. I also want to show you what is voltage and current doing. Okay, so if I plot V out versus I out, or I out add versus V out, I out time domain signal versus V out time domain signal. Okay, not like this. What it has done here. Oh, not I out, V out. It should be VC and that voltage across the switch versus the current through the switch, or switch capacitor combination, right? So current through the switch, add versus a time domain, and versus voltage across the switch in time domain. Okay. Okay, so you will see the swing, and what you see these small, this is a harmonic balances stuff. But what you see swing, okay, when there is a voltage, there is no current. When there's a current, there is no voltage. Okay, so that's what you are going to see in a class E, while all others are going to swing here. So when we design a class AB, I will show you them swinging in this active region here, right? So this is what a switching amplifier is. Okay, save changes to class E. Yes, let it be. It is as simple as that. Okay, so this was just one, and I think I have run out of the time without being able to cover the entire thing. Okay, so here I have explained you this, and then there is a mixed mode amplifier. Okay, there is a mixed mode amplifier here, which basically treats the transistor to be a voltage controlled current switch, voltage controlled current source, and for a certain part of the waveform. For the other half of the part of the waveform, it is like a switch. So most probably a class G will fall over here. Okay, so the way to design it, again, there are equations for everything. So the circuit designer has equation for every kind of stuff. It's just not class E I have been doing this circuit designer for a long time now. Okay, so I have for all passive elements, I have formulas for which are validated. So I will think about passing on this. This was my company only previously, NetTel Microsystems, when I developed this. Okay, so I'll think about that. Okay, now coming to PA specifications. So let's say we will call it the end of the day. Tomorrow, I'm going to cover very important concepts of linearity, AM, PM conversion, bit error rate, and all that stuff. So once we are through this, then we will be able to dive into system level design. Okay, so I hope that people have some interest in learning this. And I would like to have your feedback, other than, yeah, you have a demand for something which I'll put online, right? Other than that, so what I'm going to do is I'm going to unmute all. And if there are feedbacks, questions, anything, you can talk to me. I can stop the recording for now.